This is a little mini lecture on serial communications. We're going to go over three kinds of serial communications. First of all is the UART, which stands for Universal Asynchronous Receiver Transmitter. That's used in RS-232 ports, serial ports, and is used to communicate with your Bluetooth module from the launch pad for your project. We'll also talk about serial peripheral interface, which is a faster interface for communicating between integrated circuits and used for things like analog to digital converters and digital to analog converters. We'll also talk about I2C or I2C, integrated circuit communications. This is a low-speed serial communications protocol, and you can have a lot of devices connected up to the same chain. So to start out with, let's look at the UART for asynchronous serial communications. Asynchronous means that there is no shared clock between the transmitter and the receiver. The nominal baud rate must be the same for the receiver and the transmitter, so they agree at the beginning that they're going to send so many bits per second or so many characters per second. Usually is what the baud rate is the characters per second. That's what baud means. Baud means symbols per second. So each symbol could be many bits. In our case, usually it's ASCII, which is 7 bits. But there's also some bits used as overhead to make it possible to send, so you can tell where you are in the stream of bits. Baud rates should be within 1%. That means both the transmitter and the receiver need to be really close in clock frequency. There's a start bit and at least one stop bit, sometimes two, and optionally you can put in a parity bit. And that gives you at least 20% overhead. It should also be noted that the Rx of one unit connects to the Tx of the other unit, and the Tx of the first unit connects to the Rx of the other unit. So Rx goes to Tx and Tx goes to Rx, and that's a very confusing thing, but you just have to realize that it's kind of like, if you're telling secrets, you put your mouth next to your friend's ear and whisper, and he does the same thing back to you. So that's the way this works. The RS-232 protocol is shown below in the picture here. Basically, when the communications between the two devices is idle, in other words, nothing's happening, the line is high. They call that a mark, and when it's low, they call that a space. This is left over from radio teletype, which worked on a system kind of like this. And so when one device sends data to the other device, the first thing it has to do is take that high idle state and lower it for 1 bit period. That's what's called the start bit. And then there are 7 bits sent of data, and those 7 bits are generally one ASCII character. You can have a parity bit to make that 8 bits, and then there's at least one stop bit before you can send another character. Notice that start bits are low and stop bits are high, so you can have a very long stop bit that's essentially an idle. So if you see on the very bottom, there's an example of the letter M, which is 1001101. So you see the start bit goes low, and then you get the first 1, and notice it's starting at the it's starting at the lowest bit, the least significant bit. That's important to know. So it sends 1, 0, 1, and then it sends 1, 0, 0, 1, and then it puts the stop bit, which is another high. Let me see. I make sure I got that right here. This is the start bit, and then we've got 1, 0, 1, and then we have the other 1, and we have 2 zeros, and then we have the last one. Oh, and then there's the parity bit. I missed the parity bit. The parity bit looks to see how many ones there were in this thing, and we're using even parity. So if we count 1, 2, 3, 4 ones, so that's even parity, and so that means we're going to send a 0 for the parity bit. It's even parity, and then there is the stop bit right here, and it could keep on being high there. Okay, so here are some details of the UART in the MSP430F5529 and similar processors from the 5XX and 6XX family. It's interesting to notice over here on the left, we can select which clock is going to be the clock for our basis of our communications. And of course, on both the transmitter and receiver, there's a separate clock. Each one of them, you don't send the clock between the transmitter and the receiver. It's just the data, the TX and the RX, and of course ground has to be connected as well. So this part of the thing, the prescaler and the modulator, they determine what's known as the baud rate. And these clocks go out to both the transmit section, which is down here on the bottom, and up to the receive section, which is up here on the top. The inputs from the other device, here we have the RXD, that's an input from the other device, and here's the TXD, which is the output to the other device. There is a bit you can set in one of the control registers called UC Listen, which allows you to listen to what you're transmitting. There is also some circuitry in here and also down for the transmit that makes it easy to send IRDA. IRDA is an infrared protocol for sending serial data over UART. In your case, you have for your project, you have a Bluetooth module that just connects on here. But you could use an IRDA instead of the Bluetooth module. The only problem is most phones don't have that, so we're using Bluetooth. And you enable that with this UCIREN. Here you would switch between the IRDA protocol and the protocol for just standard UART. These levels out here on our chip are TTL levels, but in many RS-232 devices they make those things much higher voltage so that they can transmit over much longer distances. This thing right here is the receive serial register, so you can imagine all the data coming in, going through this line here, and it's moved into this serial register. When you finally get the stop bit, then that data is moved from the receive register up to this receive buffer, UC, and the X, of course, depends on which UART you're using, and this is the receive RX buffer here. That's where you will actually grab the data from. And the other thing that happens is, your clock comes in here and it clocks this data in, and there are interrupts that are enabled, and they're generated up here in this area, and there you can see various different interrupts for errors and other things that can occur. And there's a receive interrupt that comes from up here. And similarly, there's the transmit buffer, which you put your data in to send, and then the clock that's coming in here moves this data from from the shift register here, and if it's IRDA, it goes through this line, but we're just running it straight through here and out the TXD and going over to the receiver, the Bluetooth module. And there are some interrupts that are generated down here, and some setup bits for determining various different things. Like, say, for example, this is the parity enable bit. This tells what kind of parity you're using. This tells you whether it's most significant bit or least significant bit first. And this tells whether it's 7 or 8 bits. And you have those same bits up here controlling the receive buffer. And there are some bits in here which help you generate the right clock frequency for transmit and receive here from the clock frequency that you're using right here to run the whole thing. And you'll have to read the MSP430 5XX and 6XX user's guide to really understand what this block diagram here is showing you, but it's all there in chapter 36. A few little notes about the USCA UART initialization. When you're initializing things, you want to turn on the reset, make the reset high, so you can set up all the configuration registers, and then when you clear that thing, then it enables the UART to start transmitting and receiving. And you can, if you want to, you can get transmit and receive interrupts. I recommend this is a good way to go. It's better than polling, but you can do polling if you wish. And when you do this, enable the interrupts, that basically starts the receiving. So there's a little bit, you remember the center section about the baud rate selection, and if you're familiar with serial ports, you have to select the baud rate, 9600 baud or a 19.2 kilobaud or whatever you want. You have to select that, and this is part of the setup that you'll have to do on your launch pad. So the way it works is there's a modulator which multiplies the clock by a square wave. There's a prescaler, which is a divider, and the baud rate is a fraction. It's the modulator divided by the prescaler of the clock frequency. So if the clock frequency was 1 megahertz, and then you've got the modulator and prescaler to take that 1 megahertz clock and get the right frequency for the baud. And there is a bit called UCO16, which if you set it to 1, it means more measurements per baud interval, which is actually very good, because you see, when clocks aren't exactly synchronous, what the MSP430 does is makes a whole bunch of measurements each bit period. If you can set that UCO16 equals 1, it will give you a lot more measurements per bit period, and it's good to do that if you can. That's only possible to do. It's only possible to set the UCO16 bit equal 1 if your prescaler over modulator factor is greater than 16. And how do you figure out what to set up for the modulator and the prescaler and whether you want to use UCOS 16 or not. You use the tables in Chapter 36. There's different tables whether UCOS 16 equals 1 or whether it equals 0, so be careful. Now, a little bit about the interrupts on the UART. There is only one interrupt vector for RX and TX. Both you have to discover whether it was an RX interrupt or a TX interrupt. And you get an RX interrupt when you finally receive the stop bit, and you get a TX interrupt when you've just finished sending your last character, and now you could load a new character into the TX buffer. So just like with the timers, you had an interrupt that had many different things that could have caused it. Here we have an interrupt with two different things that could have caused it, either RX or TX. You have to determine which one it was, and if you look at the code here below, you can see that this is an example of how to do it. This came right out of the 5XX6XX user's guide. So what about examples? Well, there's the C examples from the Code Composer Studio. You can go to Project, the Project menu, and then the next in that menu there's an Examples menu, and then to filter by MSP430F5529 if that's the board you're looking for. And you can find probably I don't know, there's 8 or 9 examples there. Look for the ones that say UART on the kind of on the end. And there is also a C example on the wiki, on the Robot 2015 section of the wiki. This example is basically a little example that you could use with your phone using the handy Bluetooth terminal app. And basically what it's when you run it on your Launchpad, it asks for a password, and if you send it the right thing, it says good, you got the password. If you send the wrong thing, it says whoops, you didn't. And you can look at the code there and see what that's doing. So just a little warning, this asynchronous communications can be tricky because there's both a receiver and a transmitter, and you might have the receiver working properly, but if you don't have the transmitter working properly, it's not working. And so your logic analyzer can actually be quite useful. PulseView has a protocol analyzer you can just set up so that you can actually see the ASCII going by. So there's one other thing we need to talk about as far as UARTs go, and that has to do with what the convention is for the end of a line. So normally what you'll do is you'll receive character by character. You keep putting them into an array until you get to the end of the line, and then you want to terminate your array. That's what you do in C. And so how do you know when you're at the end of the line? Well, it really depends on what operating system you're using. Because different operating systems using different terminating characters or character. Sometimes it's 1, sometimes it's 2. So Unix, Linux, and Multics, and other similar systems, OS X, FreeBSD, etc., BIOS, Amiga, RISC-OS, and others, probably the largest portion of operating systems, newer ones, just use line feed. That's a \n in C, or 0x0a, 10 in decimal, hex 0x0a. Then there are some operating systems that just use carriage return, which is the \r in C, or 0x0d, or 13 in decimal. Examples of computers that use that are like the Commodore 8-bit machines, like the Commodore 64 and those kind of things. The Apple II family use just a carriage return. Mac OS up through version 9, OS 9 also uses that. So that's the carriage return. Then there is the RS, which is used by QNX and pre-POSIX implementation. That's not very common these days. And there's 0x9B, which was used on Atari 8-bit machines. And there's carriage return plus line feed, both of them. I think maybe Microsoft decided to use that because that way it would become somewhat compatible with Unix and somewhat compatible with the things like Apple II, because when they send a carriage return line feed, then it could be received, either one of those could receive it or something, but it still didn't solve the issue if you're trying to connect Microsoft Windows, DOS, or whatever, a CPM with one of these other things, you're likely to end up with problems. And then there was actually a few operating systems that used it backwards, line feed plus carriage return, things like the Acorn and RISC OS. So anyway, watch out when you're speaking across different operating systems. You can have some issues. So make sure you know what you need to use for the specific communication you're doing. Now I want to switch gears and look at the other two types of serial communications briefly. The next one I want to talk about is serial peripheral interface, or SPI. And this is a fast serial communication between the microcontroller and one device. Well, only one device and the microcontroller. It's useful for peripherals that generate a lot of data really fast, like analog to digital converters and digital analog converters. They either generate the data or they consume the data very quickly. And it's only good for short distances, so basically it's used on the one circuit board. You use it between chips on a circuit board. And it's full duplex. That means both both the master and the slave, the two units that are communicating with each other, can talk at the same time and listen at the same time they're talking. So in this picture, the master is on the right and the slave is on the left. It's kind of backwards of how we had it back here. Notice there, the master's on the right and the slave's on the left. So notice it's synchronous. There's one clock. The enable is optional. You can use a 3-wire SPI interface without it. SI is also known as MOSI. MOSI stands for master out, slave in. And SO is known as MISO, and SO stands for slave out, or master in, slave out. So the master usually generates the clock to determine when transfers occur. So what about the MSP430 specific features for SPI mode? Well, you can use 7 or 8-bit data length. You can use least significant bit first or most significant bit first on transmit and receive. You can use 3 or 4 pin SPI operation. In other words, you can use the enable or you don't have to. You have both master and slave modes in the MSP430, so it can be a slave or a master. You can do independent and receive shift registers. So that means, let's look up here, you can kind of, you can have independent transmit and receive shift registers. You can have separate transmit and receive buffers. You can have continuous transmit and receive operation. You can have selectable clock polarity and phase control. You can have programmable clock frequency in the master mode. You can have independent interrupt capability for receive and transmit. And the slave can operate in low power mode 4. Okay, let's switch gears yet again to the third kind of serial communication I want to describe. This is called I2C, or I2C. There are basically ground and 2 wires, SDA and SCL. SDA is the data line and SCL is the clock. And SCL is gated. In other words, it's not always running. It only runs when you want to send data. It's synchronous. There's no clock generation for the slave units. You can have up to 32 slaves. It's basically a wired OR circuit with pull-up resistors. So basically any slave or the master can pull the clock or the SDA down, and that's what happens. And basically the slaves all look at the data going by, and if they see their address is being addressed, kind of like in a classroom, when the teacher calls on a specific student, then that student responds. So this is similar to that. I2C is only good for slow speed kind of stuff, generally less than 1 megahertz or megabit per second data rate. There are details found in chapter 38 of the MSP430, 5XX and 6XX user's guide. And by the way, the SPI stuff I think is in chapter 37 of that great user's guide. Well, I hope this has been helpful. And so that's your quick introduction to serial communications on the MSP430.